Great. So as our next speaker sets up, I'll introduce him. I'm very excited to have Gabe Margolis today. Gabe is a PhD student at MIT and Polkad Agrawal's group. He's done really influential, really nice work early in his PhD on robotic locomotion. He's gotten robots, especially quadrupedal robots, to do really amazing things, to run really fast, to big jumps. And since then, he's also expanded his work to other areas like manipulation. So I'm very excited to hear what he has to say.
Yeah, Karen gave a great talk on how human babies learn to walk. So now I'll tell you some stuff that I made up about how to make robots walk. Yeah, and the title of the talk is Learning Proprioceptive Intelligence. So my research interests have emerged from studying legged robots running. And I started exploring this a few years ago on the MIT Mini Cheetah when we created the first sim-to-real locomotion controller to beat the MPC running speed for that robot. And subsequently, we explored this diverse gait generation and published this open source Walk These Ways code base that's now used by lots of labs around the world. And this talk is going to be about embodied AI, but it may be a little bit different from some of the takes in the morning that you heard about embodied AI. So a lot of work today is focused on tasks where the primary challenges are vision, language, and reasoning. But I would argue that in some ways we already have abundant data on this from the internet, and what we don't have, people are making great progress collecting through demonstration. On the other hand, another consideration in embodied AI is the forces, contacts, and dynamics that are specific to the robot that you're controlling, which you can think of as the feeling in the robot's joints, and I'll term this as proprioceptive intelligence. To be more specific, suppose we learn a policy that interacts with the environment by sending motor commands and observing sensory data. The environment, which includes the robot, might have some mass properties, contact properties, and other things that are not directly observable. An agent with proprioceptive intelligence implicitly or explicitly makes inferences about hidden states in the environment based on the outcomes of its own actions. And then these can be used to inform better actions. And actually, for the legged robots that we're looking at, they're mostly not relying on tactile or vision data for this. Their sensory data is primarily coming from proprioceptive actuators, which allow the robot to feel the motion of its joints over time. And this type of learning can require lots of physical interaction data. So in the work I'll discuss, we're using reinforcement learning in massively parallel simulation. If we look at real-life human manipulation, it's clear that humans are doing some kind of fast, dynamics-aware control. And the challenge is not that these scenes are visually or logically complex, but that the best solutions have fast or exotic dynamics. They can't be described in terms of static pick-and-place operations. So these strategies that account for the dynamics, react at high speed, et cetera, can be more performant, energy efficient, and safe. And in light of this, I'm going to zoom in on 3 instances from my work where we've incorporated new dynamic understanding into robot controllers in different ways. Let's start with robot soccer. If you've ever seen RoboCup, you'll spot that most of the approaches adopt a planning and sort of open-loop execution paradigm, where the robot walks slowly to the ball, lines up a kick, and then kicks the ball hard before chasing it. This is very different from human strategies, where the human will run with the ball and apply repeated corrective contacts. So how about we encourage our robots to adopt the same strategy? Then they could possibly manipulate on in-the-wild terrains like grass, pavement, and snow. One idea is that we can apply the paradigm of learning to infer and have the policy learn to overcome uncertain perception. However, we find that this is necessary but not sufficient for the dribbling task. Another idea, as in locomotion, is to randomize and infer the friction between the robot and the ground. But this is also not enough for dribbling. We found that it's critical to infer the dynamics of the ball itself. In particular, if you think about kicking a ball on pavement versus thick grass, if you kick it on pavement, it's going to sort of roll forever. If you kick it on thick grass, it's going to slow down very quickly. So the robot doesn't know what terrain it's on. It needs to infer this drag from the ball's motion, as well as the type of kick that it just applied. And we found that this combination is the key to unlocking agile dribbling behavior. So as you can see on the right, we have an overhead view of our legged robot manipulating a soccer ball. It takes as input the ball velocity command, and it's using its whole body to achieve the desired motion. And our system is robust on diverse terrains and succeeds at repeated trials and autonomously controlling the ball along a prescribed out and back path. So we have pavement, grass, sand, and even snow since we're up in Boston. So now we've taken our diagram of proprioceptive intelligence and expanded it with object properties as part of the inferred state, as relevant in a manipulation task. But adding this new task raised some questions for me regarding the inference that's going on. So we've made the robot run on ice and drivel on ice. But when it's doing each task, does the robot know, for example, what the friction is? Does the robot need to know what the friction coefficient is? And what if I change the task? Like we saw for driveling that we need to introduce a new parameter, drag, that wasn't relevant for running. To concretize this problem, suppose we have a drone image and we want to choose the best path for the robot to take. We might ask, how should the robot prefer paths given different tasks, such as free locomotion or dragging a payload? One idea is to collect terrain labels from a proprioceptive traversal and learn to make visual predictions on the untraversed terrain patches. So when the robot walks across patches of terrain, it'll label them with the friction that it feels, and then learn a vision module to predict the friction on new terrains. But a subtle challenge with this is that even if the environment parameters are task agnostic, the estimates are usually task specific. And let me show you why. If a robot walks on a low friction ground, its foot will slip, and this yields information about the friction coefficient. But if a robot walks on high friction ground, there may be no slip, and in this case, there's no information revealed from the state history about the friction coefficient. Therefore, the labels from walking on a high friction domain will be biased and not predictive for a new task like dragging, where the high friction does matter. Our insight to resolve this is that instead of optimizing for a particular task, we can provide the policy with an estimation reward. Now the robot's actions are actually being optimized for estimation performance, leading to intentional information gathering during the skill. In practice, this means that the robot learns to intentionally rub its foot against the ground while it walks to better observe the ground friction parameter. And we see that this leads to more accurate and less biased predictions across a wider range of terrains. So this doesn't make the robot better at walking, but what it means is when we pilot the robot across diverse terrains, it can gather more accurate labels of the terrain properties. And the vision module that we train as a result makes more accurate predictions that are relevant for new tasks. So now we can solve our problem of labeling affordances in a drone image and plan distinct paths for different walking and dragging tasks. And the execution shows that the preferred paths are actually more optimal because you slow down on grass when you're dragging a heavy box. You don't slow down while you're walking. So why did this work? Well, fundamentally, the robot rubs its foot on the terrain, then estimates the reaction force implicitly somewhere in the neural network based on its proprioception. And this is intriguing because it suggests we can learn to infer and control the applied force on these robots. So we can ask the question, can we isolate and study this force estimation and generation mechanism a little bit more? And to do this, we consider the task of whole body teleoperation for a quadruped with a mounted arm. So suppose the robot touches an object. A human teleoperator's hand will keep moving, but the robot's end effector encounters resistance. How much force will it apply to overcome the resistance? In prior works, this is generally undefined. The robot might fall over, it might comply, or it might be super stiff. So our formulation trains a policy to match desired force levels based on proprioceptive feedback. The robot learns in simulation to adjust its posture to exert different forces against an external force field, matching the input to the network that's provided by a user. And at deployment time, we can implement algorithms like impedance control or gravity compensation on top of this that perform some logic on how much force is being applied given some displacement. So leveraging the force control policy, we can implement a variety of modes, including gravity compensation, a fully compliant mode, and impedance control. So here's the fully compliant mode where my collaborator Tiffany drags around the end effector of the robot with it not being given any command other than to comply. Here's a gravity compensation demonstration. So we have the robot lift some massive object, and then if it's not told to support it, it drops. If it's told to support it, it supports it, but also remains compliant. And finally, when we implement the impedance control mode, we can even drag a heavy object across a room. So in summary, I've described 3 ways that we set up learning problems to explore proprioceptive intelligence. And in each case, a proprioceptive algorithm emerged to map the proprioception data to a reactive behavior. So if you're curious about any of these projects, you can find more information at the QR codes, and I'm also happy to talk at the poster session. So thanks for listening.
About a very interesting talk, I just have a very quick question. When you further like the physical parameters of the ground, what do you think the actual information you get beyond semantic label? For example, just notice that grass, this is like some ground, like something like that. Do you think like you can, like what kind of like actual information you get from directly using the vision module beyond the semantic labels?
Yeah, thanks. So the question was how can we get extra information through this method compared to using semantic labels for the terrains? So I think one example of how this can give extra information is, for example, let's say that on one day there's dry ground and then the next day it rains and the grass is wet. So even though the grass appears the same, it might actually have a different physical property. And in that case, you might want to collect some new data. You know, if there's data that if I can collect data today and train a vision module based on that, it might have a prediction that's actually accurate to the current environment that I'm in, compared to a sort of semantic model that doesn't capture those types of ambiguities or variations.
So let's thank our speaker again. All right, so while our next speaker gets set up, I'll introduce him. I'm very excited to have Dinesh Jayaraman speaking here. Dinesh is a faculty member at UPenn, where he started in 2020. Before that, he was a postdoc at UC Berkeley, where I had the pleasure of getting to know him and work with him. And before that, he was a PhD student at UT Austin. And actually, as a grad student, Dinesh actually started in computer vision. And one of the things I really like about his work is he has really interesting ways of using perceptual data to do real robotics. And since starting as faculty, he's also branched into other areas like active exploration, active perception, and exploration. So I'm excited to hear what you have to say.
Thank you, Andrew. I'm really honored to be here. What a great set of talks we had already today, and I hope that you will also similarly enjoy my presentation. So as the title of this talk suggests, I'm going to be speaking in roughly equal parts about what we can do to exploit today's prevalent principles in robot learning, and also about exploring, once we've pushed the limits of today's prevalent trends, how do we explore better design principles to think about what the next generation of robotic AI will look like, right? So let me start by kind of talking roughly about what I think of as today's conventional wisdom in robot learning, which is that scaling is going to take us very far, nearly all the way to fully embodied AI is really kind of the noises that you're beginning to hear from industry, for example, right? Industry is placing really big bets on what I think of somewhat unkindly as brute forcing robotics, but it's really about scaling data, models, and compute. And so, in this family, you'll see, efforts like the Google DeepMind RT family, the OpenVLA family, Octo, and so on and so forth, right? And this is really about exploiting what works best today. And we have a kind of repertoire of tools that we've developed in the field over the last few years that have begun to work really very well. So imitation learning is one of those tools. Sim-to-real-RL, like Gabe was showing, is one of those tools. Exploiting and developing the advances in our sister disciplines like language and vision, especially the foundation models that are able to perform well in unforeseen, unseen environments, zero shot. That is another important kind of set of tools that we've developed. And so this is exciting because there's lots of lowish hanging fruit, lots of clever system building work to do, and many new robotic capabilities to uncover that we couldn't have dreamed of even a few years ago. So there's a lot of excitement around this, and there should be. I'm very sympathetic to the idea that we should be exploiting. But as I'll kind of, to foreshadow something that will come later in the talk, I want to also push for exploration as well. But let me first talk about exploitation, where here's an exhibit of what we've recently managed to accomplish, which I think is really exciting. This is a paper that we just wrapped up a couple of weeks ago for generating essentially policies that can operate entirely zero-shot on new robots in new scenes with new objects, because these policies are trained with no reference to any one robot, any one scene, any one set of objects. They are trained instead from web human videos. You're training literally policies on human videos, such as the ones that you're seeing on the left here. And we have many such repositories of videos, thanks to the computer vision community, right? So could we learn such general skill policies without specific reference to any one robot, scene, or objects? Here is a rough sketch of what we're doing, and you will see in yellow the names of many, what I think of as foundation models / algorithms that we're building on to achieve these results. So what's going on here is, if the video will play, there is a scene that is being first observed through an egocentric camera, and that scene is then being reconstructed using quite classical approaches, structure from motion approaches, and one of which is cold map. And using that approach, we can now ground also with the state-of-the-art and hand detection, the movements of the human hands in 3D. And that tells us something about how the human hand is performing relative to actual entities in the scene. Having seen that, now we can train a diffusion BC policy. This is another in the repertoire of tools that I spoke about. We can train a diffusion BC policy that can essentially learn to operate a human arm. Of course, we're never going to actually get to operate a human arm, but we're going to pretend and train this entirely offline on human data to operate a human arm. And you'll see that it's doing a reasonable job. It's actually kind of pointing in the directions that you would expect the human arm to move, right? And then, once again, using another set of models, like AnyGrasp, which is a kind of off-the-shelf foundation model for grasping. You can think of it as one of the foundation models that exist in robotics. And also work from our colleagues at CMU called VRB for finding affordances. We can then literally retarget those human arm policies onto robot arms. And it works really rather well. So we've found that operating with these skills are in the gray boxes, operating in entirely new scenes. This robot has nothing to do with the policy that was trained, and the objects are not seen in the training data because the objects are just random humans doing random things in their daily lives. We are able to actually perform these coarse-grained manipulation tasks zero-shot with about 60 to 80% success rate in most cases, right? And so this is kind of one way of building potentially a reusable set of skills that can then be downloaded onto your favorite robot in your environment, your home, etc. And this is something that I'm really excited about. But the takeaway from this is that we can kind of, using these foundation models, using the fact that we have models now that are beginning to actually work in computer vision, in robotics, in language, we're able to get a bunch of background knowledge that then permits us to operate with minimal or no fine-tuning in new contexts, right? So here is another exhibit of producing cool results through scaling. This is a little quadruped that we call Hopper, very similar to the quadrupeds that Gabe was showing you earlier, which is walking on a yoga ball. This is a fairly audacious task that my students pitched to me, and I said, don't break my robot, please. And they somehow did manage to get it to work. And we were quite surprised that this happened, and we were very proud and showing it off all around campus at Penn. And you'll see that it's the same method is deployed not just on this robot, but also for in-hand manipulation of a cube and so on and so forth, right? And all of this is done through scaling simulated experiences. So we now have simulators, thanks to folks like NVIDIA, that are very large parallelized simulators that allow you to gather large amounts of experience at one go. And this has had applications in locomotion, dexterous manipulation, and many other robotic tasks. And in particular, here is the kind of simulator that we were training our robot in. So Sim2Real is another really important toolkit in the arsenal of scaling robot learning. But unfortunately, Sim2Real, and hopefully Gabe will back me up on this, it requires a lot of cumbersome manual design and domain expertise, right? It requires things like reward function design. That's the first thing that anybody who's trying RL who thinks, okay, RLs produce lots of cool results. Let me try it on in my lab. The first thing they trip on is reward function design. It's really, really hard to do. Even an expert usually does it through trial and error over many weeks, and so on and so forth, for any reasonably complicated task. And what we're showing with the yoga ball is a very complicated task, right? So reward function design, environment design, domain parameter choices, all of these are manually engineered over many weeks, months, really. And here are examples of these choices as reported in the appendices of papers that are kind of producing really cool Sim2Real results. So we asked ourselves, okay, can we somehow help this along, make this a little bit more automatic, make the burden on the human RL engineer a little bit less by using large language models. And so the key idea that we exploited in a series of papers is that we can, in fact, use LLMs together with simple iterative search, like evolutionary search algorithms, that can then help to automate sim-to-real RL. So LLMs can be prompted in plain language and using some description of the environment in terms of the simulator code to generate reward functions in code. It can be used to generate domain randomization hyperparameters in code. It can be used to generate a curriculum of training environments to develop a very complex skill over time. And all of this is done not by directly trusting the outputs of the LLM, but instead taking the outputs of the LLM as initial candidates and then refining it over several rounds of iterative search. So this work was led by Jason Ma, who's a PhD student that's graduating and will soon be on the faculty market, and I hope that many of you will look out for him. Also, Will Liang is a senior undergraduate student who will soon be on the PhD student market, so he will be applying for PhD programs as well, and I hope that you will consider him for your research groups as well. So here is roughly the system. We have a task and a safety instruction, both expressed in natural language. Here the task says, if you really squint, it says, to make the Go1 quadruped balance on the top of the ball. And the quadruped should maintain a z position of 2 times ball radius or higher, something very simple, right? So it's really just an expression in plain language. And then the safety instruction says, please keep in mind that the policy will be deployed on a robot in the real world. As such, you should prioritize safety, robustness, and so on and so forth. And then we have this approach, the system that I described, which is called Eureka, which essentially helps to design the reward function. And then also, in a series of papers, we built this out to say it's going to design the domain randomization parameters. It's going to help design the environments that you train on, the physical parameters of the environment that you train on. And in that process, we obtain these policies that can then be deployed in the real world. Here are some examples where we are a little bit braver than the videos that I initially showed, where we are no longer kind of wrangling the robot, but allowing it to kind of do its own thing. It doesn't stay on forever. It only stays on for about 15 seconds at a time. But even so, that's beyond what I thought was possible. And I hope maybe that Karen is kind of more impressed by this than the other robot learning results that we've seen so far, or other robot learning results that you've seen so far, right? Maybe this is something that maybe an 18-month-old can't do, or we rather wouldn't want them to try. And then here is us being mean to the robot in various ways. In this particular case, we deflated the robot, kind of inadvertently, actually, but then it led to a cool video, so we kept it. And as the robot deflates, as the ball deflates, the robot continues to balance, right? Here is a follow-up, which is going to be presented at Coral, where Will and Sam here are demoing the robot on an entirely unseen obstacle course. And this is the kind of setting where we needed the LLM to generate a set of training environments of increasing complexity, a curriculum of tasks. So the LLM would help us in simulation to design an increasingly hard sequence of courses over which you would train the robot so that then when deployed on a new course, it had picked up all the right skills, like leaping onto a ledge or leaping across a little a gap and so on and so forth. And then eventually it could be deployed onto a new scene that we had constructed in the real world. Okay, so all of this is to say things are really beginning to work. We really should be excited. But I do want to say there are limitations to brute force robotics. One of the most common ones that's brought about is that's brought up is that it's hard to get coverage of the target data distribution. But this I think of as kind of if you throw enough money at this, maybe this problem will go away. There are ways to get simulations. There are ways to get lots of teleoperated data, etc. But I think there are more fundamental blind spots. There are resource inefficiencies in ways that don't really affect, for example, vision or language. Scaled models bring up immediately in the context of robotics resource inefficiencies. And resource inefficiencies are something that we can't afford. They stare you right in the face the moment you touch a robot. This little quadruped that we're walking on has very limited compute on it. It has very limited power on it. If you put it on a drone, it has even less of all those resources. And you need to be cognizant of those resource inefficiencies. Safety and interpretability, ease of acquiring new skills, all of these I think of as kind of fundamental blind spots. And we should be, particularly as the academic community, thinking broadly not just about exploiting, but also exploring new principles that will help us overcome these kinds of blind spots of scaling, right? And the one that I'll focus on today is resource inefficiencies, because I think it's very fundamental, and that it will eventually constrain this kind of optimistic-looking curve about what brute forcing robotics can do to make it a little bit more like this. It'll instead kind of taper off with time. We'll find that actually once we start to want to put AI on robots that are operating real-time and very dynamic tasks with very limited resources, that we'll have to come face-to-face with the fact that our scaled models don't really work. And so we should be exploring better principles, and in particular, I like to frame this as minimalist and efficient robotics, right? So one way to motivate this is that, like in all of engineering, well-designed artifacts should be no more complex than required for them to perform well, and robotics is no different. You can look then at biology and say, today's robots versus simple yet highly capable animals. Think of crows and jumping spiders, even C. elegans. These are ridiculously simple organisms and yet can perform highly complicated physical functions. And that tells you that clearly we are not operating at the limits of how little complexity we can have in order for an agent to perform well. So we're clearly missing good design principles. And I think that one of the key places to ask questions is understanding the resource performance trade-offs of robots. One kind of question, and I'll motivate one kind of question that we've been asking very soon, right? I like to think about robots as essentially devices that convert sensed information about the world and produce physical work. What's going on inside the robot, if you peek in, is a bunch of information processing computations. And information processing is bound to destroy information, right? And so one way to think about what we need to do when we are designing a robot, what the design principles should be, is we should be thinking about which information to selectively sense and retain at each internal stage of computation inside the robot. And so while the brute force approach is to sense, remember, represent, predict, and plan all of these internal computations as much as possible, and it's kind of largely, I think, a relic from a time when these were key bottlenecks in robotics. We couldn't really do any of these very well for a long time, but now that things are beginning to work well, it's time to start kind of pruning down, is my argument, right? So minimalist design requires understanding trade-offs amongst task performance, sensed information, compute, training data, so that we can then focus our bounded cognition on the robot, the bounded resources on task-relevant factors. So here's the type of question that we've been asking. And this is really kind of a question that's very dear to my heart. It's not the first time that anybody in the field is asking this question, but people have been asking these questions since the late 90s. Matt Mason and Bruce Randall Donald had really nice papers in the early 90s about what we should do to reduce our dependency on sensing. But the question I'm asking is, what does a robot learner need to sense and attend to at each stage of computation to learn and perform a task? And how does this vary as a function of task characteristics, agent characteristics, and learning phase? This is really one of the first questions that I set out to answer as I started my job at Penn. And so the very first paper that we published, in fact, after I started at Penn, is about measuring the relationship between the degree of partial observability in a very simple task, a cart pole balancing task, and the difficulty of robot learning in this setting, right? So here we have a very controllable degree of partial observation where you're allowed to observe only up to a certain height on the stick, and it turns out that observing up to a certain height on the stick creates a very tunable knob for how difficult the control task becomes. If you were able to observe it all the way up to the very top, then it becomes a much easier task. But if you're only able to observe the first centimeter or so of the stick, it becomes suddenly a very, very hard task in a way that can be characterized critically. It can be characterized through control theoretical approaches, right? And so this produces known limits on our ability to control these robots, and we find that those known limits on the ability to control the robot in standard control theory, in a standard control theoretic framework, they actually map also to the difficulty for reinforcement learning, policies that then balance the stick. So we've been kind of digging into that kind of question a little bit more recently, and one that I'll highlight in some detail now is a question that is, or a version that's asking the question, how valuable are extra sensors to a robot? So this is a paper that was published earlier this year at iClear, and Edward Hu at the top right there is the student that led this work. So we created a bunch of simulated environments in order to answer this question, how valuable are extra sensors to a robot? We created a bunch of simulated environments in each of which we had two clones. One of those environments at the bottom only functioned with very simple sensors. So you would only have, for example, proprioception for a cheetah that is looking to traverse a fairly complex terrain, right? Another of them had extra sensors that we call O+, that are going to permit, for example, visual sensing in each of these cases. So there are really, really hard tasks if you're trying to accomplish them with just baseline sensors. What we're going to do is train 2 RL policies, one that operates from the diminished set of target sensors, O-, and another that operates with the help of these additional sensors like vision and so on. Right? We'll call them pi plus and pi minus. And now, if you plot the performance of those methods, then it's not very surprising. Policies trained with the extra sensors do indeed perform uniformly very high across these tasks, and policies trained with fewer sensors do indeed perform uniformly very poorly across all of these tasks. So we had a set of 10 tasks, and across all of them, we found this to be true. But now, can we conclude that these tasks cannot be performed without these additional sensors? And the answer to that question is, surprisingly, I'll try to convince you, no, because actually, the value of the extra sensors comes largely at training time, not at policy execution time. And the understanding here will become, or the meaning of this will become a little clearer over the next couple of slides. So what we did was we said, OK, let's create a setup where even though at test time we're going to deploy these policies only with a very diminished set of sensors, without vision, a blindfolded robot trying to jump over obstacles, et cetera, we will still at training time provide access and exploit these additional sensors that we were considering as the expanded set of sensors, right? And so at training time, so the method that we call a scaffolder, the idea is that we will at training time exploit in all the various components of reinforcement learning that are only there to help improve the policy, such as the world model, the exploration policy, the representation, the value function. All of these are components that only exist in reinforcement learning as part of the training apparatus. They all go away when you deploy the robot in the real world, right? And so you can then, in each of these components, exploit all of these additional sensors that you had access to. You can think of this as using additional sensing to distill training signals in a better way to improve the policy. Right? That's broadly the high-level idea. Let me give you like a very brief version of what the technical approach looks like. If you're operating with very diminished sensing, so here is kind of, or maybe let me back up a little bit. Model-based RL works in the following way, right? We try to maximize the following objective, where we say we're going to dream up various rollouts inside a learned world model inside the robot. We're going to dream up a lot of experience and then optimize our policies in that dreamed up experience, right? And that's really what this equation is trying to communicate, the expectation over synthetic trajectories of the reward of a policy, right? So we generate all the synthetic trajectory, and then we score the various rollouts, and then use that to drive policy improvement, all inside our dreams, right? And now, if our robot is blindfolded, if you're operating with impoverished sensing, then what happens is that all of this is affected. All of this becomes less high fidelity. The experiences that we dream up are no longer as true to the real-world physical dynamics. Our ability to score those experiences, to say which experiences were better behaviors and which are worse, is also affected. And as a result, the policy improvement gets quite slow. And so what we then propose, as I was foreshadowing on the previous slide, is that we will train the world model instead on the additional observations, the scaffolded full observation set, including things like vision. And that turns out to do the trick in terms of you can still imagine now for a blindfolded policy, you can still imagine its dynamics, its rollouts in higher fidelity. You can produce better experiences, and you can score those behaviors better with the right value function. And all of that leads to improved policy learning, right? And so that's really effectively how this is going to work. And it turns out, this is kind of like the core nugget of the paper, but we also have other components that can be improved, like the exploration policy, the representation learning objective, and so on. And I won't get into that too much, right? But once we've done that, then when we now measure what happens in the same set of tasks, we find that really almost all of the gap between training on O plus and training on O minus, training on the expanded observation set and with the diminished sensor set, nearly all of that gap is made up by our approach. About 80% of that gap is essentially made up by that approach. So one way to think about interpreting this is that about 80% of the value of extra sensors to the robot comes at policy improvement time, at learning time. It comes from improving the ability to learn, not from improving the ability to execute a skill, which I think is a really interesting scientific finding. And so one corollary of this is that as you get more efficient at a task, a robot can also as you get better at a task, you can also get more efficient at it. Okay? So learning requires more sensing than task execution. And we've actually exploited this principle in a few other ways. This is a paper that won the Best Paper Award at Coral also involving Ed and a master's student, Kun Huang. In this case, we were using privileged interactive perception, where we were able to use interactions with the environment, forceful interactions with the environment, to determine whether our policy is in fact making progress towards a task, such as in this case, locking a door properly. And so you can see that you're kind of like learning these interactive behaviors that nudge the door to see whether it is in fact locked, and that leads to better behaviors in a range of tasks, such as in this case building a stack of blocks, and in this case tightening a screw, and so on and so forth. And that leads to better policies. Eventually, policies that can actually check their work a little bit, where they kind of first try out the task and then pull it and see whether it works or not, and then when it doesn't, they try again, and in that process, they succeed. Right? Okay, so this broad principle of paying attention to the right sensors, in this case, the right sensed information from the world, can be injected beyond sensing into other control modules as well. I broadly break down the perception action loop into observation, representation, and then decision making or action. And one way to think about what's happening inside a robot is that information is getting generated in the environment, right? And that information is then getting filtered through a variety of sensors into the observation, which is only capturing a subset of the information. So already at this stage, like I was showing in the previous few slides, you can be deploying the right sensors, or you can be looking at the right areas of the world to gather task-relevant observations. So that's one broad bucket of the work that goes on in my group. You can be retaining task-relevant and interpretable information at varying levels of detail at the representation stage that then follows the raw observations. And then at the decision-making stage, you can be thinking about attending to key events, to key image regions, and so on and so forth. So how much time do I have? Maybe another 10 minutes? Okay, all right. So I will then show you an example of how we can retain task-relevant and interpretable information at varying levels of detail. So this line of work starts from a question: can a representation be optimal for robotics? And my argument is going to be that this is not a very well-formed question, because different aspects of the environment state are relevant for different tasks. No one state representation can be optimal for all tasks, right? And so this is not, we're not the first people to notice this. It has been noticed in other works before, like Akil and Soto 2017, Naftali Tishby back in 2000, and so on, right? And our answer to this problem is that we should be training not a single representation, but instead families of representations that then provide affordances for various tasks downstream. So you can think of them as providing coverage in terms of task optimality for a really large space of tasks. This will become clearer over the next couple of slides. We should be able to condition some pre-trained task-relevant representation, not just on the input raw observations, but also on the task that we're trying to accomplish. So this produces a task-relevant image representation, and it represents in my mind a way to reconcile the fact that we are moving towards pre-trained models, pre-trained representations, and so on, and yet we want to have the flexibility of performing a really large set of tasks afterwards. And so the only way to do it is by making that pre-trained representation encoder conditioned in some way on the particular task that you're trying to accomplish, right? So this has some echoes in recent work, this broad principle of constructing a task-relevant image representation. But our approach to this is, I think, somewhat unique, where what we're trying to do is build representation families that are organized by the discrete semantic entities that compositionally make up our world. We want to organize representations by objects, parts, subparts, and so on. These are, in fact, the actual discrete physical entities in the world that we need to pay attention to. And so you can think of a representation that's organized something like this, right? Where for a particular object, you could then zoom into that object and produce various key points on that object, and then zoom further into that object and get even more high-fidelity information about the folds on that object, and so on and so forth. So, for example, how you would use this in an actual laundry folding task is that you would say, here's a pile of laundry, let me first pick out one garment on it, and when I pick out that one garment on it, I only need to look at that area of the world in high detail, and everything else can be relegated to a coarse representation. Now I need to then, having picked out that garment, figure out which fold to make on it, and that requires paying attention to a set of key points on it, and then so on and so forth, right? So as we progress through a task, we recursively improve or iteratively adjust our attention to focus on the right task-relevant regions of the scene. So here is an instantiation of these ideas in a series of papers. First, we wrote a paper on how we can use foundation models for segmentation, which are increasingly becoming very, very good, to first identify all the objects in the scene, then notice for these among these objects which of them are named in a task description provided in natural language, and then build a representation that uses a pre-trained image encoder to embed each of these segmented regions in the scene, and then provide it as input to a policy. And we found that that already provides some advances. And more recently, we've been working on an iteration of this, and actually in collaboration with Bernadette, we've been working on an iterative improvement of this, where we don't just deal with objects as kind of one level of representation, but kind of go further towards that picture that I drew on the previous slide of the shirt being represented at varying degrees of resolution. And so we say, for example, that there are these various objects in the scene, but these various objects themselves contain parts and so on. And depending on what we are trying to accomplish, for example, placing the kettle on the stove, we can then identify which parts of the scene need to be represented in high resolution, and then which other parts can instead be represented as just a coarse background. And so that, it turns out, is a very powerful principle. It leads to lots of improvements in behavior cloning tasks, in imitation learning tasks, in both sim and real environments. We find that we are working substantially better than various alternative representations that don't adopt these kinds of object-centric and task-conditioned principles. And then we find further that you can do systematic generalization because you're now focusing your policies on just the parts of the environment that matter to you. So any changes to the background, like the color of the table becoming blue instead of white, matters much less to you because your policy is not really conditioning on it as strongly, right? And that principle can then be exploited further to then accomplish long sequences of tasks, where we can say, we trained a bunch of low-level skills, all starting completely independently of each other, but then afterwards, I've seen a recipe for how to prepare an eggplant. Usually, you wouldn't normally be able to chain these policies together because the starting distributions of the various policies are not aligned with the ending distributions of the previous policies. But because we are robust naturally to distribution shifts, then we can accomplish these kinds of skill chaining tasks entirely without adjusting the initial set of policies that was learned. Okay, so this is really about kind of this idea of injecting attention into various components of the control loop. And perhaps the last thing that I'll talk about very, very briefly is about how you can also think about it in the context of action or decision making. We've been thinking about this problem for a long time. So, for example, we've found that when you're doing imitation learning in a car driving style task, if you focus on the right keyframes at which decisions are made, you can avoid various pathologies in imitation learning. So a very simple pathology that we've noticed was that if you just do plain naive imitation learning, where you're observing sequences of frames and then mapping them to actions, a common pathology is that it will tend to repeat its previous action all the time, rather than trying to predict what the future action is or reacting to anything that's happening in the environment. But if you're able to identify frames, and we have developed methods for doing this, if you're able to identify frames where something important changes in the environment and focus on that, that's a kind of attention over the training data that then helps you learn better policies. We've also done this kind of attention not just temporally, but also spatially, where we can use similar kind of entity-centric representations of objects to very quickly learn from demonstrations, from a very small number of demonstrations, how to perform tasks like these. We've been recently, in this example at the bottom right, learning how to dynamically allocate resources. If you have a limited amount of computational resources on a robot, and you must decide how far ahead to plan, for example, these are questions that can be answered by carefully thinking and training meta policies that allocate resources on your robot so that you can perform dynamic tasks like grasping moving objects and so on. Okay, so I'm going to start wrapping up. What I've really been arguing for is that rather than only exploiting today's principles like scaling, which we of course must do, just to push the limits of what can be already achieved, and clearly there is a lot that is to be achieved, we should still also be exploring better principles. We should be thinking in particular about what we can do for constructing more minimalist robots that resemble more the kinds of functions that we can see in biology, right? And robotics is at an exciting moment. We should be simultaneously exploiting, pushing the limits, and exploring. And in particular, the kind of question that we've been asking is about selectively attending to important info at each stage of training and control. And I really want to say, many, many fundamental questions in robotics remain unanswered. The kinds of questions that I was motivating earlier about, what is the sensory information that we actually require to perform a task? Even a simple question like that you can ask in like 10 words is still hard to answer. And this is despite us having explored this discipline for 60 years. So this is not a solved field. There's a lot of exciting work to do. And let us all take it on together.
Thanks for the very nice talk. We have time for a few questions.
Hi, thanks for the amazing talk, first of all. I just wanted to ask about, so in the earlier part of the talk, you talked about minimalist robots and basically decreasing the amount of observation necessary to its minimal state. But in the latter part of the talk, you talked about like having task-specific or hierarchies of representations that inadvertently like blows up the volume or the amount of representations that you're like solving your tasks with, right? And I couldn't help but notice that like this sort of like goes against each other in that like you would try to decrease the amount of observation, but coming up with all these hierarchies of representations and task-specific representations also like increase the amount of resources and energy required to come up with them, right? So I want to
Thank you
hear
for the question. Yeah, I think I understand where you're going. I would say the implementation of that kind of like course-defined structure where we can decide which parts of the scene we actually require fine-grained representations for is indeed an implementation of the idea of economizing over which parts of the world to sense. There are mechanical details to exactly how this is implemented, in terms of a sequence of representations for various objects, etc. I wouldn't claim that we are at the limits of how efficiently we can implement this, but we are still, broadly implementing that idea that we should really only require sensing at high detail, a very small region of the scene. So to give you a sense of this, if we were trying to perform really high precision tasks, let's say like folding an object, folding a cloth that requires sensing like the little folds on the cloth and so on. You would, in order to be able to represent this without the principles that we're talking about, you would need a very high resolution image. And all of a sudden now you're talking about a really, really high dimensional representation. And what we're doing then is saying that kind of really high resolution representation really only needs to be applied to a very small region of the scene. The rest of the scene can still be represented in coarse detail. That's broadly where I think this work is heading. I will concede that we're not at the most optimal implementation of that idea just yet. Yeah.
Let's thank the speaker again. A great talk. We have one more speaker before the posters. So while the speaker gets set up, I'm very excited to have Ilija Radosavovic presenting today. Ilija is a PhD student at UC Berkeley, where he works in Jitendra Malik's group. And even before being a PhD student, he had some very influential work in computer vision, and specifically around recognition. Since then, he's done a lot of really exciting work with robotic locomotion, making humanoid robots walk in all sorts of places you wouldn't expect them to be able to walk. So very excited to hear what you have to say, Ilija.
Thank you very much, Andrew, for the kind introduction and for the invitation. Really happy to be here, and thank you very much everyone for coming. So today I would like to tell you a little bit more about the work we've been doing at UC Berkeley about how we might approach robotics as a sequence modeling problem. And a sequence modeling problem using a particular type of data. And these are sensorimotor trajectories. So what I mean by that is I mean a collection of sensory and actuation measurements that we get over time as the robot is interacting with the environment. And I'd argue that we can really view this data as being the language of the physical world. So in the remainder of this talk, I'd like to show you a few case studies of the work we've done and on how we might exploit this data to form rich representations of the physical world that enable robots to act in the world. But to start with, I'd like to simplify the problem a little bit and forget about perception for a while and really focus on these sequences of proprioceptive and actual observations to start with. So here is a video showing our humanoid robot walking around Berkeley. So this is a full-size robot developed by Agility Robotics. We don't build the hardware, we develop the learning algorithm and the software for this robot. So it's a full-size robot, about 160 tall, about 45 kg. And it's being controlled by a single neural network that's running on board. It's entirely blind, it does not use vision, it only uses proprioception. And this neural network can control this robot to walk. And it really is a fully end-to-end learning approach where the neural network gets the past sequence of proprioceptive observations and actions, and then it predicts the next action. So very much like in Gabe's and Dinesh's work, this model has been trained in simulation over thousands and thousands of simulated environments And the intuition here is something like this, which is that if we can train a single neural network controller to control thousands of robots in slightly different simulated environments, then perhaps we could think of the real world as being just another simulated environment. And then once we have this model, we can transfer it to the real world zero shot without any additional training or adaptation in the real world. This robot can perform omnidirectional walking, though not quite as elegantly as babies do that we've seen in Professor Karen-Edelf's talk, but it can move in all directions. And one peculiar thing that we've noticed is that this robot is swinging its arms a little bit like humans do. And we were kind of curious, okay, why does this happen? It's kind of interesting. And it turns out that there are a lot of studies in biomechanics on why humans move their arms, and there are many theories that are proposed, but sort of seems most likely that this is to preserve energy. And in fact, one of the optimization objectives of our robot is to minimize energy while walking. One study we've done on adaptation is, I think, really interesting, and especially interesting to discuss after we've seen Professor Edelf's talk, because it has to do with this adaptation to different environments. So here we have our robot walking across 3 sections of a terrain, so starting with flat ground, then going down a slope, and then continuing back on flat ground. So let's see what happens. So the robot first starts off by lifting its legs. Then once it reaches a slope, it sort of adapts its gait to use small steps. And then when it goes back to flat, it starts lifting its legs again. Now in this case, this is reactive because the robot is blind. But what's interesting is that we have not pre-programmed this behavior. We have not encouraged this behavior in any way. This behavior has emerged as a side effect of learning to walk. And our theory really is that this is due to this, the in-context learning or in-context adaptation ability of these sequence models that are trained on these sensorimotor trajectories. So the robot is able to adapt its behavior based on context. And we try to do some sort of probing of the neural representations learned by this model, and we see indeed that the representations naturally cluster based on these terrains. So in summary, we've seen a fully learning-based approach that can perform in-context adaptation and enable a humanoid to walk in real-world environments. Now, the natural question is, can we extend the same method to more complex environments? Can we deal with terrains that are less gentle, that are more uneven and more challenging? And in principle, yes, we could use the same technique. We could make our simulations more expressive. We could include various terrains in simulation. We could repeat the same thing. But in practice, this tends to be challenging because of many factors, including the more complex task, more complex reward engineering, like Dinesh was talking about. And these tend to be sort of reinforcing, which makes this overall endeavor challenging. So we take a step back, and sort of in an alternate approach, we train the same architecture, the same sequence modeling problem, but now instead of reinforcement learning, we use sequence modeling. So we sort of train this model to walk based on a prior data set of trajectories. So no interactions with the environment, purely offline data set of past trajectories. And we have gotten the same architecture to control a robot, again, to walk in the real world. Here I'm showing some clips of our robot walking around various locations in San Francisco. And I won't have time to go into details of this paper, but you can sort of view it as an alternate training strategy. Now, if I'm to compare and contrast these two approaches, compared to reinforcement learning, this is much more sample efficient and much more stable. But the downside is that it can only be as good as the data. So we have this chicken and egg problem that if we only have the data of walking on flat, we can only get a model that walks on flat. And then the natural question is, can we get the both of best worlds? So in our most recent work, we studied this in the context of locomotion over challenging terrains. And we propose a 2-stage approach for learning to walk. So in the first stage, we first pre-trained this model with sequence modeling on a data set of trajectories of walking on flat ground. So this serves as a really useful starting point that we can obtain very quickly and efficiently. And intuitively, a model that is able to walk in gentle environments should be more efficient at acquiring new skills thereafter. And indeed, in a second stage of learning, we then fine-tune this model with reinforcement learning, with via interactions with the environment, and we train it on various uneven terrains. So here we see discrete obstacles, slopes, and so on. And so now, because we're starting from a pre-trained model that's already has some working capabilities, this reinforcement learning step tends to be a lot more efficient, and indeed orders of magnitude more efficient. So really to test how well does this work in the real world, we took our robot on 5 different hikes in Berkeley. So collectively, our robot has hiked over 4 miles of trails in the Berkeley area. And here are some examples from various hikes. So it can handle all sorts of uneven terrains, rocky terrains, rutted terrains, slopes, and sort of the combinations of those. And then we performed another case study where we evaluated our robot on steep streets in San Francisco. So we went to various different streets, and I'm showing the slopes here in the top left of each image. So some of these are really, really steep. The streets with over 30% grade tend to be really hard even for healthy adults. And what's interesting all this is that the model has been trained only on slopes of up to 20% grade. So a lot of these grades are out of distribution and unseen during training. And here are some clips of the robot going up these roads. And another interesting thing is that we've trained this model only on rigid environments and simulations, so only planes, only sort of concrete slopes. But then at test time, we've deployed it to a beach. So it has never seen sand or anything deformable, anything soft. And the model has been able to generalize to these environments. And we conjecture, again, due to the in-context adaptation ability of our sequence models. The model is also pretty robust to various disturbances. So we can push it while it's standing on uneven ground. And it's able to adapt its actions to maintain balance. One interesting thing we've seen, again, is the sort of these representations that are indicative of different terrains form as a side effect of training. So here I'm showing neural representations while the robot is walking over various different terrains, so be it flat, uphill, downhill, and we see these clear clusters emerge depending on the terrain that the robot is walking on. And again, same as before, none of this has been pre-programmed or encouraged or supervised in any way. These are entirely emergent as a byproduct of learning to walk. So we've seen that we can sort of train a humanoid robot to walk over challenging terrain via this 2-step procedure with pre-training via sequence modeling and fine-tuning with reinforcement learning. And then here's some videos, and the paper are available on the website. Now I've started this talk showing the sensorimotor sequence, and really a big part of this is vision and perception. It's pixels, it's high-dimensional data. So I'll show how the same principles can apply in manipulation with learning with pixel and sensory observations that are more high-dimensional. And some of this work was presented at Coral last year. So here's how a typical sort of sensory tuple looks for a robot. So we have a couple of images, we have proprioception, we have action. But then we also have this all over time. And then as the robot executes, we get this sequence. And now what we can do is we can take this sequence and we can mask out subsets of this sequence. And then we can train a model to predict the missing content based on the present parts. So let's look at the whole sequence once again. So we have a sensorimotor sequence. We mask out the subset of this sequence, and then we train a sequence model to predict the missing parts. And sort of really at the core of this method is sensorimotor prediction. And the intuition here is that if a robot can mentally in-paint the missing parts of the environment, it has likely acquired an implicit model of the world that should enable it to act, and it should make it more efficient downstream. And indeed, there's a lot of evidence in human motor control and learning that prediction is really key to motor control as well as understanding at large. So given this model, we can then use these shared representations to learn new behaviors downstream. So we can fine-tune this model with a little bit of task-specific domain data and then obtain a policy that can then be used to perform robotic tasks. And at inference time, we can roll out this model auto-regressively. So we we predict actions, we execute actions, then we feedback actions as well as the new sensory observations together with back to the model context, and then we repeat this in a sensorimotor loop. So here are some simple manipulation tasks that this can do. But more importantly, what this enables is transfer across robots. That is, in this case, different, same types of robots, but in different labs. So what we see is that we can pre-train on a robot model in one lab, and then we can transfer these representations on the same robot, but in a different lab. So note here that there is a discrepancy in different tables, different environments. Camera locations are different, and there are certain differences within the hardware as well. But what's even more interesting is that we can do this across different robots. So in this case, we pre-train our model on a robot, on an X-arm robot in one lab, and then we fine-tune it on a Franca robot in a different lab. And on the right-hand side, I'm showing you some quantitative comparisons, and I'd like to make two observations. So one is that we see that pre-training leads to considerable improvements compared to training from scratch. But what's perhaps more interesting is that it comes very close to pre-training on the same robot type, which is a promising signal for this kind of cross-robot transfer between different environments. So we've seen that we can use real-world sensorimotor trajectories that include vision and high-dimensional pixel observations and use them to also to enable manipulation as well as cross-robot transfer. So in summary, I presented this view of robotics as a sensorimotor sequence modeling problem, and I presented two case studies on humanoid locomotion and on manipulation with vision. And we've seen that this approach can enable various robots to perform control tasks, and it has some interesting properties like in-context adaptation and enables pre-training. So thank you very much, and please check out more details on my website.
Great. So we have time for one quick question while the next speaker is set up.
I have noticed that the simulator you use is Isaac Jim, right? So the digit have some spring mechanism and parallel mechanism. So how do you overcome this symmetrical gap? Because I guess why Oregon State University use Mojoko as their simulator. So how do you overcome this symmetrical gap?
Yeah, so we used the Isaac Jim simulator in some of our early work, and we came up with essentially manual modeling for some of the constraints that are not supported by Isaac Jim, sort of a poor man's simulator on top of Isaac Jim. But in later work, we've also explored Mojoko, and because our method has become more sample efficient, so we're now less reliant on the speed of the simulator, and we can also train in Mojoko. Thank you.
Let's thank the speaker again for the very nice talk.